Hello everyone, welcome to IMS GATE Academy. I am Atul Negi and we are discussing the foundation course on fluid mechanics. In the last class, we have discussed regarding the fluid dynamics, okay, in which we have discussed the basic fundamentals of the dynamics and we have discussed the Navier-Stokes equation, and we have also solved some previous year questions from the Navier-Stokes equation, right? So Navier-Stokes equation is very important, and if you have not watched that particular lecture, so you should first watch that lecture also, so that you will have a basic understanding of dynamics as well as the Navier-Stokes equation. Now in this lecture, I will be discussing the Euler's equation and the Bernoulli's equation. So we will derive the Euler's equation so that you will have a basic understanding how it is derived, what are the things we have assumed in the derivation of Euler's equation, and we will see the applications also for the Euler's equation as well as basically the Bernoulli's equation, right everyone? So we'll start our lecture here, okay? So fluid dynamics, Euler's equation. From the Euler's equation we are going to start, right? So as you know that in the dynamics part, what we are going to discuss the force, right? We are going to discuss the forces apart from the motion related parameters. So force is what very important part, because force is the only reason because of which the substance or any particular body is what moving. So we need to do the analysis of the force as well while doing the analysis of motion. So motion analysis we have done in the kinematics. Now force part. In the last class also, I have discussed regarding three equations: Reynolds equation, Navier-Stokes equation, and the Euler's equation. So if I just ask you, what are the forces that we are going to consider in this particular Euler's equation? Can you tell me? What are those forces which will be considered in the Euler's equations, and which are the forces we are going to neglect? Those forces also you should know, okay? So pressure and the gravity forces are there that we'll discuss in Euler's equation. Remaining forces like turbulent forces, compressibility forces, surface tension forces, all those forces we are going to neglect. Yes, Jatin Gupta, absolutely correct. Correct, absolutely. Great. So those two forces we are going to discuss here, okay? So according to Newton's second law, I will directly writing this pressure plus the gravity, okay, equals to mass into acceleration. So that is what our Newton's second law, okay? Now I will be deriving the equation of Euler's equation using this thing only. A very good evening, Tirumala. So what I will consider here, I will consider a small fluid element along the streamline, and we'll do a control volume analysis for that small fluid element, okay, regarding to subject which that fluid element will be subjected to various forces like pressure and the gravity forces. All those forces we are going to discuss. Now see, let's suppose a streamline. Let's suppose this is a streamline, and in this streamline, let's suppose if I take a small fluid element, so this is the fluid element that I have considered here, okay everyone? See, right, this is a fluid element that I have considered here, so you can say it is a streamline. So along the streamline I have taken a one fluid element. Now I will draw this fluid element separately here, okay, so better clarity. Okay, now see, very important part. So this is the our fluid element, okay? Now you have to tell me what are the forces, okay? First of all, the pressure forces will be there and the gravity force, that is what the weight. So let's suppose along the stream length, if I assuming this length as a ds, small ds, ds is the length along the streamline first of all, and you can consider the area as dA, small area, right? So this is the small area dA, okay, correct? Now I will show you the pressures forces. First of all, here I will show the pressure forces. So this is the pressure force. I can write it like this: P into dA. Okay, some pressure force will be acting here. Now, in order to write the pressure force here, I will be using the Taylor series expansion formula, right? So how I can write here? See, pressure plus dou P by dou S, okay, into ds This will be the pressure into area, pressure, force, right? I hope this point is clear, everyone. We have used this formula in the kinematics and the statics also various times, right? So this are the pressure forces. Now second force is the gravity, that is the weight of the fluid element itself. Okay, now if I have to tell the fluid weight of the fluid element, I can tell like this. Mg will be the weight. Okay, mg. Now how to write m, mass? Instead of writing mass, I can see, basically I will write here, instead of writing mg, directly I will write the value of the mass here. What will be the value of the mass? Density into the volume. Density and the volume will be what? dA into ds. Okay, into g. So this thing obviously it is clear that this is what? M. This belongs to what? M. Density into dA into ds is the volume. So density into volume, mass, mg. So pressure, force, this weight also we have discussed. Now, so as let's suppose one more thing I can assume here. So let's suppose, assuming this angle to be theta. Assuming this angle to be theta from the center line, this angle is theta. Correct. Now, very important point, as the length along the streamline is ds, okay, and this angle from the vertical is theta, correct? Let us assume the vertical depth to be dz. Vertical depth to be dz. Simply I can assume this thing. Okay, so this vertical depth from the center point is what? dz. I can assume like that. Correct? So what is this value here? Then it will be, see, this is ds along the streamline. Very important point. Along the streamline I have taken. Now if I talk about the velocity, velocity will be a function of the s along the streamline, the space and time. Velocity will be a function of space and time. Correct? I hope this point is clear to everyone. So this basic fundamental thing you should be like clear about. Like velocity is a function of space and time. Space along which the streamline is here, that is space. S stands for the space and T stands for time. So we are taking a very general scenario here, okay, and we'll take further assumptions, we'll take further, right? But first of all, we will derive the equation in a very general way, okay? A general equation we will derive, then we'll apply certain assumptions also, like steady flow is there, okay, incompressible flow is there, like those basic assumptions we will apply in the later part. But in the starting, we will discuss everything, right? I hope this point is clear, everyone. Tell me fast. Tell me, correct? Okay. Now, so Es, and if I have to write dz, let's suppose dz in terms of ds, so I will be writing ds cos theta. Correct? ds cos theta will be there because if you take the cos component, you will be getting this one. Okay. Now, I hope up to this point everything is clear. Now, what we are going to do here next? We will apply the Newton's second law. We will apply the Newton's second law for this particular fluid element. Okay. So, we will apply the Newton's second law. Right? Any doubts, guys? Please tell me fast. Any doubts? No doubt? Okay, great. So, applying Newton for Newton's second law for fluid element. For fluid element. Applying Newton's second law for the fluid element along the streamline. Very important. Okay, along streamline. Very important point. Okay. Now, we will apply the Newton's second law. So, Newton's second law, we will write it like this. Summation of forces equals to mass into acceleration, and the directions of the forces will be along the acceleration part. Correct. Now, what are the forces? See, along the streamline, pressure force, and this is also a pressure force. Correct. And we need to take the weight along the streamline because we are writing the forces along the streamline, right? So, you have to take the component of the weight along the streamline. That will be what? W cos theta. Okay, simple. Mg cos theta we can say. So, first of all, pressure. P into dA minus P plus dou P by dou S ds into dA, okay, plus, okay, we will put a minus here, mg cos theta equals to mass into acceleration. So mass, how to write mass? We have just written here. See how we have written mass? Density into dA into ds. That is what mass. Okay. And how to write the acceleration? I hope you remember the point. Dou v by dou t plus v dou v by dou s. So this will represent our acceleration. I hope this much basics are clear, right? So, so like in this direction, downward direction, I've taken negative. So that's why this weight component will also be in the downward direction. So we have to take it negative. So PDA, then this force, then the component of the weight along the streamline. So all the forces we have taken, and it is equals to mass into acceleration. So just for your better clarity, I will write it here itself. This term will represent mass. This term will represent acceleration. Correct? Okay. Now, see. So now, if you just simplify this equation, what you will be getting? Minus dou P by dou S ds dA. Okay. Instead of writing mass m, I will be writing rho dA ds. Okay, into g into cos theta. Right, and we'll write it as it is. Dou v by dou t, dou v by dou s. Correct? I hope this much is clear, everyone. Now, if you see a very important point here, what I have written, ds cos theta as what? dz. Okay, dz we have written. So ds cos theta is there, so I can write dz here because I want to have this height in a vertical direction. That's why I am preferring the dz because it is in the vertical direction. But if you talk about the ds is along the streamline. Okay, so in order to make it simpler, I am taking in a vertical direction. So I will change this ds cos theta as what? dz. Okay, so minus dou P by dou S ds dA minus rho dA into this dz will come cos theta. Okay, and g will also be there. Okay, we will write g also here. Rho into g. Okay, so ds cos theta I have taken as dz. So cos theta will not come. Correct? Okay, now see. And here as it is, it will be there rho dA ds. Okay, and dv dou v by dou t plus v dou v by dou s. Now let's suppose, now I will be taking assumptions now. Let's suppose if I am taking a steady flow condition, if I will be taking a steady flow condition, because that is what the most common assumptions that we are taking in fluid mechanics. Most of the cases belongs to steady flow. So let's suppose if the flow is steady flow, obviously this term will not be there, dou v by dou t, right? This component will not be there. Okay, now see. So let's suppose if I am taking for steady flow, okay, for steady flow, dou v by dou t equals to 0. Correct? That thing we will implement in our equation. Right? So minus dou p by dou s ds dA. Okay, and what is there? Rho g minus rho g dA dz equals to, right, rho dA ds, and it will be like v dou v by dou s till here everything is clear? Tell me everyone. Any doubts regarding whatever we have assumed and how we have come to this much step? Okay, this step is what very important. Now, initially we have not assumed anything. Now we are taking some assumptions here. Okay, now we will be taking some assumptions. So I hope this much is clear, everyone. Jatin, if you are there, please tell me everything is clear, yes or no? Clear? Now, if you just focus on the equation, the last equation that we got in this, if you observe, pressure and the velocity are function of S, that is space, because we have assumed the steady conditions, right? So I can say now pressure and velocity are function of, that is space. So whatever the partial differentiation I have written, I can call it like a simple differentiation. So that partial differentiation becomes basically the total differentiation then, because it is a function of S only. So instead of writing dou P by dou S, I will be writing dP by ds. Correct? Dou V by ds, I will be writing dV by ds. Simple. Okay. So that partial differentiation becomes the total differentiation because it is a function of single variable, not the multiple variable that was initially there. Okay. Now the whole equation becomes the function of, basically the pressure and velocity becomes a function of single variable, that is space. Okay, that point is what very important. Otherwise you will be thinking, okay, dou V by dou S is written, so we can write dV by ds. No, it is not like that. We should understand when we can write such things. Okay, so now as pressure and velocity, PV is what the pressure, V is what velocity, right, are function of S only. Okay, so we can write, so we can have the total differentiation. We can have a total differentiation instead of the partial differentiation, right? Any doubts in this point? Because that is what the basic mathematics, right? This much mathematics is what required. So you cannot think about fluid mechanics without mathematics, right? Then you will be studying theory only and you will always find difficulty in numericals and the derivation part. Because of the mathematics only, the study of fluid mechanics becomes simple, right? Mathematics actually help us to analyze the fluid flow. Without mathematics, it is impossible to study the fluid motions, right? So this much basics mathematics you should be knowing. Okay, otherwise some difficulty and the problems will be there and you will be always be in a confusion. Okay, you will be always have some confusion. So what we have written, pressure and velocity are function of S only. Now we can say the partial differentiation becomes the total differentiation. So like that we can write. Okay, so simply I will tell like this. So we can have, partial differentiation become total differentiation. Okay, so partial differentiation becomes the total differentiation, and okay, right. Now, so we'll write it in the next step. So dou P by dou S becomes minus dP by ds. Correct? Whatever dou P by dou S written, it is now becoming dP by ds. So ds into dA minus rho g, okay, rho g dA dz equals to, okay, rho dA ds and your V dV by ds. Now from this you can easily cancel out the ds term here. This ds term will cancel out here. This dm term will get cancelled out, right? This is clear, pretty much simple. Now see everyone. So what is the equation now? You will be having minus dp into dA minus rho g dA dz equals to rho dA v dv. Now please try to focus here. If I divide the whole equation with density into dA, if I divide the whole equation with density into dA, finally what I will be getting? Tell me. So it will be like minus dp divided by rho, okay, because the dA is already there, so minus dp by rho minus rho g, rho into dA. So you will be having g dz, because rho dA is already there, so it will get cancelled out, equals to rho dA is already there, so you will be having v dv. Now if I take all this term towards the right side, what I will be getting? See, dp by rho plus v dv plus g dz equals to 0. That is the what equation I will be getting, and that is what our Euler's equation. Okay everyone, this will be our Euler's equation. I hope this much basics is clear. So this is what we are having as a Euler's equation. Okay, this is what we will be having as Euler's equation. Right? Clear everyone? So this is what we are having as the Euler's equation. Now again see how we have derived this equation. This is what we'll be having as a streamline, along which I have taken a small fluid element. This is my fluid element. For that fluid element, I have seen what are the forces involved. So basically for the Euler's equation, I will be taking pressure and the gravity forces only. So pressure forces, gravity, that is weight we have taken. Okay. Most importantly, velocity is a function of space and time, that is we have taken, and applying the Newton's second law. Applying the Newton's second law for the fluid element along the streamline. Very important point, along the streamline we have taken. So that's why the weight component I have taken along the streamline, right? Because we are applying Newton's second law along streamline, correct? Okay, so this is what we will be having as a fluid element. Correct? Now after that, Newton's second law, force equals to mass into acceleration, I have applied. Forces I have written on the left side, and the right side, mass into acceleration. This is the mass, this is the acceleration. In the kinematics, we have discussed in detail how to write the acceleration part, right? If you have any difficulty, please check the fluid mechanics playlist, and you will be having a lecture. You will see a lecture having kinematics. In the kinematics, I have discussed regarding velocity and acceleration separately. I have discussed. Okay, material derivative, all those basic things I have already discussed. So you can just watch the playlist, and the playlist you will be having one lecture as velocity and acceleration. You can watch that lecture also. Now, this is what the basic mathematics simplification I have done, and then later I have assumed steady flow, dou v by dou t becomes 0. So after this thing, dou v by dou t that we have taken, okay, next is what dou v by dou t we have taken 0 for the steady flow. Then the equation, because of this condition only, the equation will be what, like pressure and velocity are function of space. Now our pressure and the velocity becomes a function of single variable. That is the important point here. And because of that, the partial differentiation become your total differentiation. And because of that, if you observe, the ds sum cancel out from the whole equation, and in the terms of dz we are getting, that is what the vertical height. Vertical height. Okay, so this is what our Euler's equation. So finally we have derived our Euler's equation. Now second thing is that what is Bernoulli's equation? Bernoulli's equation is just the integration of this Euler's equation only. Integration of the Euler's equation, right? Any doubts, please guys tell me first. Is there any doubts? Any doubts? Okay, so next we will integrate this equation. If we integrate Euler's equation, assuming density to be constant, that is incompressible, assuming density to be constant. Yes, see, it is applicable for both compressible and incompressible, right? Absolutely. But I will integrate the equation assuming density to be constant, that is incompressible. Now, if I integrate assuming this thing, what I will be getting? So, first I will be writing the ILS equation dP by rho plus V dV plus G dz equals to 0. Because if I take the density not as constant, then definitely density will also be a function of a space. Density will also be a function of a space, right? Space basically means what? The location. So in that case, I cannot simply do the integration. I need to know how it is varying with respect to location or the space. That's why, right? Now, so if I integrate it, what I will be getting? So it will be what? Pressure by rho. Here we will be getting V square by 2, and here G Z equals to integration of 0. It will be what? Constant. Right. So what we got here, that is our Bernoulli's equation. This is what we are having as a Bernoulli's equation. Clear, everyone? Any doubts? Tell me. P by rho V square by 2 plus Gz equals to constant. Now, we can represent that Bernoulli's equation in different forms. Okay, we will see the all forms of Bernoulli's equation, right? So, here I will be writing Bernoulli's equation, right? Bernoulli's equation. Now, most of the important question in the interviews also, they will be asking what are the assumptions you have taken in order to derive this Bernoulli's equation. And this Bernoulli's equation represents what? Conservation of energy. Mostly students will say conservation of energy. That is correct, but not completely correct. I will tell you why. Because when I say conservation of energy, and if I simply tell energy only, it means it includes all the energy. No, which is wrong. Are you getting the point? It is the conservation of energy, but not the total energy. It is a conservation of mechanical energy only, right? So we cannot say simply like it is a conservation of energy, because we have to be what specific regarding the energies. So we are saying it is a conservation of energy, but that energy belongs to the mechanical energy, not the total energy, right? So you need to understand the difference. Okay, tell me this point is clear, yes or no, everyone? Correct? Okay. Now, some assumptions we'll be writing here. For steady flow, for basically Bernoulli's equation. Okay, first point. So that is the first point is what? The steady flow that we have initially taken while deriving the Euler's equation only, right? Steady flow. Correct. Second, incompressible. That means we have assumed the density to be constant. Okay. And obviously, what are the forces we have considered? The pressure forces, gravity forces are considered. Right. Fourth, in viscous flow, we have taken, right? In viscous flow taken, right? Correct? Yes or no? Please tell me fast. steady flow, incompressible pressure force, gravity force we have assumed, and then we have taken the in viscous flow, right? And second thing also important here, like we have taken the fluid element along the streamline. Okay, we have taken along the streamline. So you should also mention that point. Okay, now correct. So like Pragya is asking stored form of energy. Like see Pragya, you need to understand this point, the concept of energy. We can say stored form of energy also and energy in transition. So energy in transition, in order to understand what is stored form of energy, first of all you should understand energy in transition. Energy in transition means the energy which is giving to the system. System basically means our fluid here. The energy is what giving from the, let's suppose, any external agent like pump. Through pump we are supplying some amount of energy. That is what energy in transition. From outside we have supplied the energy to the fluid, right? So that will be energy in transition. But what is stored form of energy? Which is there for within the fluid itself, right? Are you getting the point? So those points you should aware of. Like see, from the term itself, stored form of energy, the energy within that particular fluid itself. But if I use pump, so from external source I am giving some energy to the fluid. Okay, so that is what energy in transition, because it crosses the system boundary, because that basic part we have discussed in thermodynamics also. So both are totally different. But if we talk about this one, so what we are saying, energy which is stored in the fluid, like within the fluid itself, that particular energy will be there. Okay, not from external source we are providing some energy. Not from external source we are providing any energy, right? So that is what the stored form of energy. Okay, so these are the basic points that you need to understand. Okay. Okay, anyone knows the fee structure of classroom program in Bangalore? See, you can just there is a number mentioned in the description box also, and there is a link also. You can directly go enter those link here. Those links are provided in the description box. Please check those description link, and there will be a number here. You can directly call and you will have all the information regarding the classroom program in the Bangalore, Jayanagar. Right. So I hope up to this point everything is clear. Is there any doubts regarding whatever we have derived here? Okay. This basic diagram is what very important. This diagram is what very important. Correct? Any doubts? Till here, any doubts? Tell me first. Okay. So regarding any admission points, like in the description, separate link is there. You can just check out those links, and number is also provided. You can directly call on that number also. Right, everyone? Now tell me, Euler's equation and the Bernoulli's equation is clear? Okay. So now we have derived the Euler's equation also. We have derived the Bernoulli's equation. Now we will be seeing, we'll observe the different forms of Bernoulli's equation, because most of the time we'll be doing mistakes here. Okay, different forms of Bernoulli's equation. Now we will see the different forms of Bernoulli's equation. Okay, different forms of Bernoulli's equation, right? See, the first format that we have derived here is simply P by rho plus V square by 2 plus GZ. Okay. Now, if I divide the G also in the whole equation, okay, just let me correct it again. P by rho G. So I am taking the G also. So V square by 2G. Then plus Z it will be there, and equals to constant. Now the unit for this equation is what? The see, energy per unit meter. Okay, Newton per meter divided by what? See, this is what the energy per unit weight. Again, Newton will be there. So finally you will be having as meter, and which is also known as head, which is also known as head. So you can understand what is their unit, energy per unit weight. Energy per unit weight. So this form you should remember. Okay everyone, energy per unit weight. This form you should remember, right? So this is the first format of the Bernoulli's equation, correct? So previously when we have derived here, you have observed like P by rho is there, V square by 2 is there, GZ is there. So what I have taken, I have divided the whole equation with G. So what it will be there, P by rho G, V square by 2G plus Z only. So that is one format of equation that we should remember, correct? Any doubt? This is what most common format of Bernoulli's equation, and we should know what is the unit, energy per unit weight. Energy per unit weight. So energy unit is what, Newton meter. For weight, Newton will be there. So Newton will get cancelled out, only meter will be there, or simply we can say head. So pressure head, kinetic head, datum head. Like that we are defining. See. So I will mention the point here. Pressure head. This is what? This belongs to pressure head. Then kinetic head. Datum head. Correct? Now, second form. Sir, this is which type of pressure head? Static pressure head, Pragya. Yes, it will be a static pressure head. Okay, this will be the static pressure head. I hope this is clear. I think you are asking about this one, right? This is the static pressure head. Correct? Tell me. You are asking for this one, na? So it is a static pressure head. Okay, now one more thing. In this equation, you can write like this also. Piezometric head. Now, can you tell me what is piezometric head? This will be a summation of static pressure head and the kinetic head. P by rho G plus V square by 2G. V square by, the datum head we will take, not the V square by 2G. Datum head. Datum head. So this is what the most common head that we will observe in any fluid flow. Piezometric head. Static pressure head plus the datum head will be known as our piezometric head, and this head will be what using. This head will be using in most of the numerical problems, right? In the flow through pipes. Okay, in flow through pipes, this is what the most common thing that we are going to use it. So whenever, remember this point, whenever the velocity is same, we will be observing this pressure head and the datum head summation, which is piezometric head. This piezometric head is what more important and becomes very important in upcoming chapters like flow through pipes, right? So summation of static pressure head plus datum head, correct? Okay, next thing. So mention here the static pressure head also, otherwise you will be having a doubt. Clear? Which type of head? Pragya, it is piezometric head. Static pressure head, this is static pressure head, this is kinetic, and this is datum. And a summation of static pressure head plus datum head is piezometric head. Correct? Now, the second format. P by rho plus V square by 2 plus GZ equals to constant. Now, for this, what will be the unit? Can you tell me? Can you tell me the unit here? Energy per unit mass. This is the unit. Energy per unit mass. Correct? Correct? Yes or no? V square by 2G. Kinetic head, Pragya, it is the kinetic head. V square by 2G will be the kinetic head. Correct? Now, Pragya, that point is clear, yes or no? Okay. Now, tell me, energy per unit mass. Yes, see, when I say kinetic, kinetic is itself a dynamic. So we can say dynamic head also. Correct, absolutely. There is no problem about that. We can say kinetic head also and dynamic head also. Both are same. Dynamic means what? The motion. And what is kinetic? Same thing, na? So that is what dynamic we can also say. See, I will tell you one important thing. Like when we study the fluid kinematics, in which we'll be discussing the motion related parameters. There is also one more thing, fluid kinetics. But this term is not that much famous and we will simply say fluid dynamics. So kinetic and dynamic both we can say, because fluid dynamics is what more popular, that's why it is what used in the books also. Otherwise we can say kinetic and also in dynamic, there is no problem about that. But as the basic understanding of engineering mechanics, you should know dynamics will have a two part, kinematic and kinetic. Okay, so dynamic is the main heading under which kinematic and kinetic will come. Okay, next. Next thing, very important. P plus rho V square by 2 Now tell me the unit for this one. Tell me the unit for this one. Tell me the unit for this one. Energy per unit volume. Now can you tell me what this particular parameter stands for? Rho V square by 2. Pragya, tell me what is rho V square by 2? What is rho V square by 2? So as you like told dynamic, so I can say it is a dynamic pressure. Because see, we should be aware of how we can write the Bernoulli's equation in different formats. So let's suppose in the equation they have mentioned energy per unit mass, energy per unit volume, or energy per unit weight. So we should know how to write our Bernoulli's equation in different formats. Okay, but otherwise most common equation is what this one that we are going to use in our upcoming analysis of the fluid dynamics. So we'll be using this one, but at least we should be aware of all other formats also. If someone asking like whether you can write it in energy per unit volume or energy per unit mass, if all those things are there in the question, we can easily use it, right? Apart from that, see, this term is very important. You will see the application of this one also. This is what the dynamic pressure. And we will call simply this one as static pressure. Right. Now, see, next thing very much important, modified of Bernoulli's equation. Modified form of Bernoulli's equation. Because in the Bernoulli's equation, we have never assumed regarding the losses. But in actual, we know that some losses will be there when the fluid is what flowing. Reading the point. When the fluid is what flowing, there will be some losses. Pragya is saying why? Pragya, I think you will be asking for this dynamic pressure. See, what we have written here, kinetic or the dynamic head. So that thing in terms of pressure, if you observe this, the unit of this particular equation is what the pressure only. So we have considered all the energies in terms of pressure. So if I say this is a static pressure, so this is what the dynamic pressure, which is there because of the motion of the fluid itself, right? So you should understand how we have represented each term of the Bernoulli's equation. Based on that, the naming will be there. Based on that, the naming will be there. Okay, dynamic head, dynamic pressure, like this. Okay, so if the dynamic kind of thing is available in energy, so we'll write dynamic energy. If it is in the terms of head, we'll write dynamic head. If it is in terms of pressure, so we'll write dynamic pressure. Correct. So now next important thing is regarding the modified form of Bernoulli's equation. Okay, modified form of Bernoulli's equation. See, let's suppose at here the datum is Z1 and here it is Z2. Correct? Z1 and Z2 are the datums at location 1 and 2. Simple. So this is the location 1. This is the location 2. Pressure at location 1, let's suppose P1, velocity V1. Simple. Pressure P2 and velocity V2. Like that, the different parameters I've considered at location 1 and 2. Now, according to Bernoulli's equation, simply I can write the equation like this. See how I can write. Simply, I will be writing here P by rho g, okay, P by rho g plus V square by 2g plus Z is constant. So, if the value of this, all three will be what constant, whether I am writing for 1 or 2, both will be same. See how I will write this one. P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g V2 square by 2g plus Z2. So this is what the Bernoulli's equation that we have written for this particular case. So fluid flowing from 1 to 2. Now when the fluid flows from 1 to 2, definitely some losses will be there. Now how to consider that particular losses? You should understand. So now obviously very basic thing I am telling you here. Let's suppose at the entry point, that is what 1, it is having 100 units of energy. For example, 100 units of energy. Now while coming at point 2, it will not have 100 units of energy because some energy has been wasted because of the losses. Because why the losses will be there? Because there will be some resistance to flow. So some amount of energy will be utilized in order to overcome those resistance. So that's why the fluid which is coming from the point 2 or location 2, energy will not be same as whatever is there at location 1. So something, some value it will be having, some value you can take 80, assuming 20 units of energy loss. So whatever the difference of energies will be there, that energy belongs to the energy losses. That value represents the energy losses. Now, second case, assuming here, I am assuming the losses. And how I will mention the losses here? See. Assuming energy loss represented by HL. Obviously, it is again a head. So we are mentioning the energies in terms of head. So we will mention loss of head. HL belongs to the loss of head. Now, how I will use this one in this equation? Because this is for the ideal case, right? When no losses are there. When no losses are there. But in the case of losses, HL will be there. Now, how to write the equation? See. A very important thing. So losses will be there. So this is energy at inlet, this is outlet. So at the outlet, energy will be less. So this loss of height we need to add here in the outlet part. Correct. Energy is conserved. So Pragya, I think you didn't listen my statement completely. What I have told you, at the inlet or the section 1, let's suppose energy is 100. Correct. But at the outlet, we are getting energy as 80 units. So where that 20 energy has gone, that 20 energy units has been what utilized in order to overcome the resistance. Are you getting the point? So here the energy is 100, here it is 80, 20 is the loss. Why it is lost? Because some amount of energy has been utilized in order to overcome the resistance which has been what offered against the fluid flow. Okay, so there is no such thing like energy will energy will not consume. Energy will consume forever. So that is what the basic principle of nature. Energy is conserved, but whatever the energy is here, but that energy will not be here. Got it? So please be attentive in the class, guys, because even if you miss any one statement, then you will be having some wrong idea of the concept. That is biggest blunder. So whenever you are watching the sessions, you should be what fully attentive, right? Okay, no issue, Pragya. So assuming energy losses. Now how I will be using this HL value? Please see. P1 by rho g, V1 square by 2g plus Z1 equals to P2 by rho g plus P2 square by 2g plus Z2 plus HL. Correct? So this is what the modified form of our energy equation. Okay. Correct? Okay. Now I hope everything is clear. Now we will solve one question here, guys. This is the question that you need to attempt and tell me the answer. Okay, very basic question for you. Please attempt this question, everyone. So what they have given, diameter of a pipe carrying a oil and a specific gravity they have mentioned 0.85, changes from 0.5 meter at section 1 to 0.25 diameter at section 2. So section 1 and section 2 will have a different diameters, which is at 5 meter lower level. Okay. The pressure at section 1 and 2 they have given 60 and 100 kilopascal respectively. If the discharge through the pipe 250 liter per second, determine the direction of flow, that is the first part, and the loss of head. So in the question itself they have mentioned losses will be there. So I will be using the modified form of Bernoulli's equation. Correct? I hope the question is also clear and the relations that we are going to use in this particular problem is also clear. So please try and tell me what will be the answer. Everyone, please try and tell me the answer. Okay, so we'll draw the diagram. So section 1 0.5, section 2 0.25. Diameter 0.25 diameter at section 2, which is 5 meter lower level. Okay. See, obviously at section 1, and this is what section 2. Section 1 diameter is 0.5 meter and section 2 diameter is half, that is 0.25 meter. So better you should draw the diagrams and so that you will be no confusion. So section 1 and 2, 60 and 100. 60 kilopascal, 100 kilopascal pressure. Correct, 60 kilopascal pressure, 100 kilopascal pressure. And also they have given one more thing. that is the distance from here to here, right, like this. Okay, now, so all the details I have mentioned here, anything which is I have not mentioned. Okay, discharge 250 liter per second. Discharge they have mentioned 250 liter per second. Now obviously we need to convert it in meter cube per second, so it will be 0.25 meter cube per second. So why they have given the discharge? In order to calculate the velocity, area into velocity, right? You can calculate the velocity at section 1 and section 2. So discharge formula they have given, na? So area into velocity V1 equals to area A to V2. You can calculate easily because the discharge values are given. You have to calculate the value of V1 first of all, and then you can calculate the velocity of V2, because these values are what important, because we have to use these values in our Bernoulli's equation, right? So please calculate and tell me what will be the answer, everyone. Okay, so direction of flow is also not given, whether the fluid is flowing from 1 to 2 or 2 to 1, and energy losses also they have given, right? Better what we can do here, calculate the energies at section 1 and section 2. That is the correct approach. So first I will write a step here. First calculate energy head at section 1 and 2. At section 1 and section 2. Okay. So obviously fluid flow will be from high energy to low energy. That is what the biggest simple thing. Okay, that is the thing that we have known from our past also. And the flow always takes from high energy level to low energy level. Always remember this simple concept of nature. Things will flow from high potential to low potential, or I can say from high energy level to low energy level. So that is what the nature's law, right? That is what nature's law. No one can violate this thing. So first calculate the energy head at section 1 and 2. How you will calculate? We have the formula, na? So directly I will write the formula for you here. Correct. Now, what is Z1, Z2 value? So, let's suppose if I take the datum at Z2 only, so it will be 0. But for Z1, value will be for 5. I will take it as 0 and I will take this one as 5. Velocities we need to anyhow find out from the discharge value. Area into velocity, from that we can find out, because the diameters are what given. Correct? Correct. So calculate the difference of energy levels. Okay, I'm writing here as a note point here for you. Flow will take place. Flow will take place from high energy level to low energy. Okay, flow will take place from high energy to low energy. Simple. Like we will say like high pressure to low pressure, but in general we should say energy whenever the at any section energy is high and at some section energy is what low. So from high to low flow will be there. Always remember this point. In the nature, flow will be from high potential to low potential. Instead of potential, you can say energy also. Simple. Right. So this point, I hope everyone, this is clear. Calculate E1, E2, whatever the difference will be there, that will be the loss. Whatever the difference is there, that difference will be the loss. So if E1 value is what more as compared to E2, so flow will be from 1 to 2. Or if the value of E2 is what more as compared to E1, so flow will be from 2 to 1. So it depends which value is more, E1 or E2. I hope this point is clear to everyone, right? If E1 value is more as compared to E2, flow will be from 1 to 2. And if value of E2 is what more as compared to E1, so flow will be from 2 to 1. I hope the concept is clear and you can easily solve this one. Please solve this question and mention your answer in the comment box also, and definitely I will reply in the comment box, okay, if someone gets the correct answer. But please try this question and I want your answer in the comment box, right? So I will end the session here itself, and in the upcoming sessions I will be discussing the application of Bernoulli's equations. Very important. Okay, we will see the details of everything, right? Specifically, I'm talking about the Venturi meter, orifice meter, pitot tube. These are the three basic applications of the Bernoulli's equation, and we will discuss from the basics. We will discuss each and every small details of Venturi meter, so that there will not be any confusion in your mind, and also you will be prepared for the interview also. Even the interview, they will be asking question from orifice meter, Venturi meter or pitot tube, you will be able to answer it. So we will discuss up to that level also, right everyone? So thank you so much, and we will meet in the next sessions where I will be discussing the Bernoulli's application of Bernoulli's equation. Thank you so much.